My name's Jeff Currier. I'm one of the dev leads on the SQL Azure team. And I'm here to talk to you a little bit about under the hood, how we've sort of designed the service for SQL Azure, and how it kind of works specifically. So last year, we had one of our architects come down to PDC, and he spent a great deal of time talking about sort of how the backend components work for SQL Azure. Talked a lot about our mesh network that we use to sort of keep all of the nodes in the network intact with one another, how we do reliable failure detection, how we do leader election when primaries fail over and secondaries get elected to take their place, and all this sorts of good stuff. Since then, we've done a sort of pretty drastic direction change on the service as a whole. If you recall, back then we were based on a notion of this thing called SQL Server Data Services, which surface basically an HTTP protocol endpoint via REST and SOAP. And a lot of us, myself included, spent a great deal of time trying to get that to work and make that usable. Went around, took a lot of customer feedback on that and said, hey, interesting, but not really what I was thinking. So last year we did a direction change and we decided to surface up a TDS endpoint. And so really, the bits I'm going to emphasize today are the things that we've done to make that happen. So with that said, we'll start very briefly with a review. And I'll give sort of a review of just sort of the service as a whole from a conceptual standpoint. I'm not going to go through and sort of give you examples of create database and all these sorts of things. I'm assuming that if you're here that at some basic level you understand what those things look like. We'll then go through and talk about the architecture of the service, both from a network level and from a component level. And we'll go through some specific workflows of how this service actually handles individual operations that you might do. So if you want to understand how login works, how create database works, how server provision happens, we'll talk about that and we'll give you a little idea how that operates. We'll talk about service resilience, how the service itself deals with failure, how we detect failure in the system, and how we recover from it. We'll talk about how we monitor the service. What are the things that we use to detect the overall service health? What do we do to correct those things? And how do we make sure it's up and running 24/7? And then finally, we'll talk about some security considerations. What are the specific things that we've sort of tried to think pretty hard about in terms of attack vectors on the service and what we've done to mitigate those problems. And finally, we'll wrap up with any kind of Q&A you might have. So jumping right into the review, there's really sort of three main concepts in SQL Azure. Only really one is really a new concept. All the others are sort of slight twists on existing SQL Server concepts that already existed. So the first is a subscription. A subscription is really a pan-Azure concept. It's really the thing that when you actually sign up for SQL Azure or Windows Azure, that really ties all the resources that you use together into one thing. It's the way we use to tie back your resources to the billing instrument, being your credit card. You can, of course, have many of these subscriptions on a per-user basis. The obvious reason for this is you can imagine that, I'm Jeff, I work in an enterprise called Microsoft. I might have many different departments within my enterprise that each want to roll up to different cost centers for the server usage that I have. This is the mechanism we use to do that. We have a logical server concept. This isn't really a sort of a real server. We don't have folks rushing into the data center, plugging in, racking equipment on demand. Rather, it's really more of a logical thing. It's very similar to a SQL Server instance in nature, in that it's a container for many databases and gives us some way to rationalize and relate back all the information that you use back to one instance. It's also the unit of geolocation, meaning that when you walk through the provisioning process via our administrative portal, you actually select the specific region that you want your server located in. I might sign up today and decide that I want to be in South Central, which means that I'm going to be pinned from that point forward to our San Antonio data center. It's also when we do billing, we sum that all up relative to the server. So all bandwidth usage that we do is all made relevant or sort of made relative to that particular server, as are the databases that you've actually provisioned. There's a one-to-one relationship between the subscription and the server. And because you can have many subscriptions, you can therefore have many servers. User databases are pretty much the exact same as what you sort of know and love today with SQL Server, with a couple of exceptions. First is that we've restricted down the T-SQL surface area that you can use, simply because there's a set of artifacts and constructs that are present in the engine today, which we just, for security reasons, cannot expose. Sort of concrete example, you might consider DMVs as an example. You could take a look at like sys processes or something along those lines and leak out some information which might not, from a security perspective, be a very good thing. You could also call certain stored procedures which might reveal server information. Again, those all surface different points of attack for people who might want to attack the service, and as a result of that, we restrict those things down or hold them back until we can at least silo the information down to something that we feel is capable of supporting from a security standpoint. And finally, we've supplemented the default catalog views, which are present in SQL, with some that make sense for our model. Sort of firewall rules, as an example, bandwidth usage are not necessarily things that make sense necessarily in an on-premise service, but they make a heck of a lot of sense for us. And so we provide you a set of views to sort of look at, understand what those things are, and to manipulate the firewall rules that we present to you. Moving on to sort of the network topology that we have in the service. So we have an app that's running either in Windows Azure or running on somebody's laptop that's actually sending packets to our service. It could be using ODBC, could be using ADO.NET, could be using PHP, could be using a socket, frankly. Each of those packets arrive at a load balancer that we have, which is listening on port 1433, and then balances the traffic that we're sending amongst a set of front-end nodes that we have that are running a process we call the gateway. The gateway then actually acts as your sort of mediator or broker for your requests to our back-end resources. It's the thing that's actually making sure that data is siloed and is doing the translation from the logical concepts to the physical resources that we have in our service. There's a security boundary here between these two guys, meaning that they're actually running in two separate clusters. And none of the machines that you see here are actually internet-facing. The only bit that's actually internet-facing is our load balancer. So all of these machines have 10 addresses, which means they're basically not addressable to the public-facing internet. And then below that, of course, as sort of Gopal sort of went into great detail last week, or not last week, last year, we have a set of a fabric and a failover technologies down there, making sure that each of those guys in the back-end databases are capable of sort of detecting failure reliably and then promoting new leaders when necessary. So going down a little bit more into what the TDS gateway actually does. So TDS is actually a published protocol. We actually publish as part of the open protocol specification, along with a bunch of others that Microsoft has. And the TDS gateway really understands this quite well. So we do stateful TDS packet inspection for messages which are coming across the wire. We broker the login process because we understand specifically the login process in TDS. You can think of the login process from TDS's perspective as being broken into two parts. There's a pre-login step, which I go through and I request capabilities of a server. I might, for example, say that I want encryption or I want Mars support. And then it's the server's responsibility to say, I can provide that or I can't, right? So in certain cases, if you roll up to our service and say, hey, Jeff, I want to connect to SQL Azure, I don't want to use encryption, or I want Mars, we might cut your connection because that's a capability that we just won't allow for various reasons. It could be that we don't support that feature, or it could be because that thing that you're trying to do we don't feel is secure. So after you get past that step, we actually receive your real credentials, a login 7 packet. The login 7 packet, and I'll show you this in the demo, actually has sort of your real username, your password, your server name. It understands the client technology you were using to connect to us. So we would know at this point if you were connecting via ADO.NET or ODBC. The gateway also, because we're doing stateful TDS packet inspection, acts as sort of an extra layer of security. Not only is it a physical process boundary between our backend resources and sort of public internet coming traffic, we can also look at the validity of the messages themselves and see if they're well formed. Are the offsets that people are telling us in the messages valid? Are they in the right order? Are the lengths proper? All these sorts of things are things that we can do to sort of help make sure that the messages we're receiving are indeed valid. Finally, we can also sort of check to see if the state machine that's being used to govern this login process is invalid. So you can imagine that it might do something like send a pre-login packet, send a login 7.1, and then resend a pre-login packet as a way of sort of trying to confuse the service. We understand that state machine, and we can block those things from happening. The next thing that it does is the sort of physical or logical to physical translation. So the gateway itself uses a metadata catalog view to help do this mapping. So when you create, server foo, database bar, we actually know the physical node in our cluster where that resides and the physical partition that that thing is living on. And it's actually the gateway which is actually brokering that and doing that translation for you. As a result of this is really sort of one of the key things that we have for sort of enabling multi-tenant capabilities in SQL Azure. Really, from our perspective, there's a sea of partitions that are all out there, right? And it's the gateway's process to sort of help make sense of that and figure out how to request or route your request appropriately. And finally, as I mentioned earlier, it acts as a really nice isolation layer for us, sort of adding another level of defense because it's an insulation factor, another process boundary that somebody would have to hop to try to get into the service. So from a component perspective, this is sort of the way the gateway breaks down. So we can see at the top we have a number of endpoints. The first and left is sort of the TDS endpoint, and this is really the one that most people are actually interacting with. So if you're sending traffic to our service, this is the guy you're hitting. We also have a set of endpoints which are WCF based and understand SOAP. So there's an admin service endpoint, which is if you're hitting our administrative portal, this is the guy you're hitting. It's not publicly facing. It's secured by certs with mutual auth. You can't actually access it externally. It's not actually internet facing. We also have a provisioning endpoint. This is the endpoint that we use to actually support the provisioning of that Azure subscription that all the services know. Below that, to service TDS, we have a protocol parser, which helps to understand the TDS protocol itself and helps us to sort of understand and how to break out and parse the messages that we receive. And those are built on top of a set of common business log services that we use to do things like create servers, create databases, and the like. We have a set of connection management capabilities, maintaining our own caches to our own metadata partitions so that we can make sure that we're not sort of overloading the backend with connections. And then finally, again, the backend databases is always sort of provided as being sort of the real meat of where the data lives. So I thought it would be useful to kind of go through some specific scenarios. So in the first is really server provisioning. So if you have a subscription or if you have a server today, you've actually already gone through this process. And this is really driven by our administrator portal. So someone rolls up to our administrator portal, they enter their live ID. If they haven't sort of redeemed an invite code, they enter their invitation code, enter some credentials, and sort of the journey begins. So what happens is actually in this case, the gateway actually receives a provision server request. We go through and we make an entry in our metadata catalog saying, hey, we're about to create the server foo. We then go through, establish your geolocation by connecting to a live DNS service, which is a dynamic DNS service, which allows us to create alias records or CNAME DNS records. And then after that's done, the master database is created and prepared for your use. And then finally, we roll back to our metadata catalog saying that we're done. Now, a lot of steps in here that could go wrong. So part of what we do throughout this whole process is keep track of a state machine so we know where we were in case a failure occurred. It's easy to imagine that you might, say, create a metadata entry, and then the call to live DNS fails. We need to understand when state transitions are not occurring fast enough, or if a failure occurred that we knew about so that we can either resume that operation or come back and clean it up later. So just sort of graphically, it's probably a little bit easier to go through this rather than just some words on a slide. So this is sort of a breakdown of sort of what a data center might look like. So you can see at the top we have the customer's browser. We have a set of load balancers for the portal traffic for the gateway process. We have another cluster that's external to our cluster, which is representing the live DNS service. We have a set of front-end nodes, some running the gateway portal, some running our gateway process, or the gateway itself, and then a set of back-end nodes which are servicing those requests. So customer request comes in to do some provisioning. That sends a request through our gateway load balancer, and then we make that gateway process then makes that metadata entry in the backend database. Assuming that completes, we then go through and the same gateway process facilitates the creation of the DNS record. Now we go through and we make another call to the gateway load balancer to actually prepare a master database. And that goes back and we actually start the process of preparing the master database. Assuming that completes, the same gateway then goes back and updates our metadata entry saying, this database is now ready for use. So technically at this stage, if you were to log in with a new TDS connection, you'd be able to log in without a problem. The call returns back to our portal saying, presenting you the sort of server info page that you're used to where we sort of show you the master database and the user credentials, and we're kind of done. And then the call returns back and transaction's complete. So database provisioning is a little different. So you can provision a database via the administrator portal. But that's actually not so interesting. It's actually, the workflow is actually very similar to the one I just sort of went over for you guys. So you can also create a database, obviously, through T-SQL. And in this case, it's actually a little bit more interesting because the gateway is actually doing stateful packet inspection and looking for candidate messages to parse. So in this case, we receive a SQL batch message, which is another type of T-SQL message. We check that packet to see if it's a candidate for further processing, and we do this by peeking into the line itself. So some people have kind of wondered, hey, why can only certain statements be the only statement in batch? This actually turns out to be why. Because if we try to look at things like dynamic SQL and things of that sort, actually turns out the complexity goes through the roof if we're trying to deal with that. So we make these restrictions like this for this reason. So we pick out a subset of messages which match those which we want to process, like create database. We parse out the arguments for the create database command and sort of the database name and the server name and these sorts of things. And then just like we did before, we make an entry in the gateway metadata catalog saying, hey, we're about to create this database called bar on server foo. We locate a buffered partition for us to use. Now, we keep around a set of hot buffer partitions so that when people go to provision servers, it's a fairly fast experience. If we didn't do this, you'd be waiting around for several minutes as we sort of try to figure out ideal placement for a partition in a sea of machines. So that's a really kind of crappy experience from a user perspective, frankly. So we keep a set of hot buffer partitions around for people to use. We'll go through and pull from that pool one for you to use and prepare it for use. And then once that's prepared, we'll actually go back and mark that metadata, mark the metadata catalog as being complete, and you can now use that user database. So just like before, slightly different picture, but here we can see we have the gateway process running on a front-end machine. We have a master cluster which has a global partition map, which understands where all the partitions live within the cluster, and a set of back-end nodes. So a request arrives at an existing TDS session, in this case, and it just happens in this case that this is one where create database is present. We parse out that message to say, is this a candidate message? If it turns out it is, then the gateway logic actually pulls out or parses the pieces of the command that are actually interesting in this case. We then go to our master node cluster and look up where our metadata catalog lives and where our buffered pool partition lives. We go to the backend node where the metadata catalog lives and mark the entry as being one that we're about to create. We're going to create the database foo on the server bar. We then reserve the buffer pool partition from another node. And then we go back and prepare that database for use at this point. At that point, job done. Partition is capable of being logged into. As far as you're concerned, all the views and all the normal sort of language constructs you're willing or sort of you know and love are capable of being used. And then we go back and mark the database, or mark the, sorry, I missed a step. We go back and finally mark the metadata catalog as being ready, and then you can use it. Sorry, my bad. So login is a question that we get a lot. How does login actually work? So login's slightly different in the case that there's no database preparation. There's no necessarily inserts that are taking place within the metadata catalog. It's really just a read-only request. So we receive a request at our gateway with a pre-login message followed by a login 7. We take the information out of that and we use that to locate the master database and the user database. We need to locate both for credentials. So as you know, sort of login information is not stored within the user database. It's stored in the master database. And we need to have that in hand in order to validate your credentials. So after we get that and we locate where those guys live, we validate the credentials against the master database. We open up a TDS session to the backend node. And then we allow that traffic to flow all the way through to that particular user database. So it kind of looks like this. So very similar slide to what we had before, except the TDS session is not quite present yet. We receive a request on the gateway. We tease out the pre-login and login 7 packets. Gateway does that, goes to locate where our metadata catalog actually lives within our cluster, goes to the metadata catalog and says, hey, where does Tony Pet's server live? Sorry, Tony. And then goes, finds his master database, validates the credentials. Once we validate the credentials, we hook you up with or a session is then created. Traffic then comes through that session and gets routed to the target user database that we found. So I thought it would be kind of interesting to do a demo where we kind of actually showed sort of how this actually looks. And I have to confess that Dave's packet trauma or network traumas here kind of frightened me before the demo. So I'm doing this on my dev machine, so you'll have to forgive me. So here's an example gateway process like we would run in the cluster. I'm going to snap it to the side. That's the Windows 7 feature I invented, evidently. So I'm going to then connect to that, enter my password. And so we can see we got a bunch of stuff there, right? So I'm just going to kind of roll up to the top here. And so here we see the pre-login messages that we got from the client that we've been talking about, right? And we can see that in this case, customer requested encryption, which is good, we want that. And they didn't request Mars in this case. So life's great. We then, after we got past that process, we went through and we actually, because we requested Mars, we have to negotiate the certificate to use for encryption. We go through and do that. And then we received that login 7 packet that we were talking about a moment ago. And so this is the piece that's actually kind of interesting. So I can see in this case that the client's using ADO.NET in this case. I can see that they were trying to connect to master. I can see the server name that they were trying to connect to. It turns out jeff.dev.mscds.com, really original. And then the username is jeff@jeff. So some people might kind of question why the jeff@jeff. It turns out that not all client libraries actually pass us the server name. And this is actually one of the reasons why we have to do that, because otherwise we don't really know what the server name is actually to try to route for you. So if you're ever kind of curious why that is, that's why. So after we have that information in hand, we then go through and try to look up the directory entry for that guy in our metadata catalog. So you can see that here. So it turns out we're looking for server Jeff database master in this case. We found it in this case on courier dev. It's on this physical database, db2. And we can see the partition range for that guy is 0x bunch of zeros A, 0x8 bunch of zeros 14. So that's just kind of an easy example of how that works, and just to give you an idea. So after that, so that's negotiated the client bit. We then actually try to do the same thing back to the server. Remember we talked about the gateway was a level of process installation. And there actually, when you open the connection to SQL Azure, you don't really directly connect to the back end. You go through the gateway process and then act as a broker for those things. And so here's an example of us doing that. So here you can see we went to we basically sent the same messages, we replayed those back to the server in this case. So same kind of stuff. So moving on. So serverless resilience is obviously a popular topic. We've kind of gone over some different scenarios, and there's a lot of moving parts, frankly, right? It's easy to see you're sort of either crossing data center boundaries, you're crossing node boundaries. Lots of little things could happen. Nodes could reboot, drives could fail. These things happen all the time. So it's actually super critical that we use state machines to track this, and this is a fairly common thing in distributed computing. So we use state machines to track where we are in the process, along with the last time we did the state change, so that we can detect if it's taking too long for an operation to proceed, if it's something that we need to either go maybe and kill off, or it's something that someone can actually safely resume. You could have things like race conditions where two people are both trying to create the same database as an example, and there are cases in that case where you want to block things for windows of time. We also do cleanup. So if we see that a particular, say, server provisioning process has failed, we will go through and mark those entries to be cleaned up at some later point in time, and then clean up the subscription for you so you can go through and recreate that thing. Again, in this case, the use of state machines and the fact that we have we're tracking the state change time is actually super critical here for that. On login, this is probably the most interesting from a user perspective. We make logins failures transparent, so for up to 30 seconds. So if during the login process, either our metadata catalog fails over, or the master database fails over, or the user database fails over, we will keep retrying that operation and refreshing our cached location of where those things live for you automatically. So those should be largely transparent to you. Beyond the 30 seconds, I'm afraid that's just something that users are going to have to retry. Post-login, and this is actually where people spend the bulk of their time, Unfortunately, there's not a lot we can do at this point. You could have all sorts of state built up on the associated with the session, and we can't really actively reconstitute that in any meaningful way yet. So that will serve as a connection drop, and it's up to the user at that point to reconnect and retry the transaction. So from a service health monitoring perspective, we do a number of things here that are fairly common with other services, but they're worth pointing out anyway. The first is that we use a lot of cluster-wide performance counters to keep track of the system. And here we track things like the number of requests per second, the number of active sessions per second, to kind of give us insight into the load of the overall system and defines the peaks and the troughs to know when things like maintenance should be performed. We also track things like failed logins per second. This is actually a really interesting indicator for things like denial of service attack. It's very easy to say that if you see a huge spike in failed logins for one particular server, that particular server might be under a dictionary attack, as an example. And we use these perf counters in the aggregate for a number of reasons, right? We alert our operations team to do further investigations if it turns out that there's a problem, as in the failed logins example. Or we can use these to sort of make some guesses about maybe code issues. So you can imagine as an example, and maybe this is a trivial case, but if you're starting to see that you're seeing a large number of failed database provisioning, right, and you had just done a deployment, it's fairly easy to correlate that there might be a code issue there. We might need to go back and figure out why. And then finally, we've used this for capacity warning as well. So I mentioned earlier that we kept a set of hot buffer partitions around for us to use during the provisioning process. We've actually seen cases, this actually showed up in the CTP, where there was a lot of demand, and we were basically running out of space on the cluster, and we had to sort of up that up. This was actually one of the things that was the canary in the coal mine that sort of alerted us that we were not able to keep up, and we had to sort of go back and add capacity. So all these things together turn out to be a really good thing, give us a lot of insight into the system. The next thing we do is around sort of service, what I call service execution, but it's really, there's a set of agents that we have running on both our front-end cluster and on the back-end cluster that are each exercising regular jobs. And these do all sorts of interesting things, it turns out. So on the front end, we do jobs that basically try to use the service in a manner that's very similar to the way our customers would use it. So we do things like we create tables, we drop tables, we insert records, we update them, we create databases, all these sorts of things. And we use these in the aggregate to say if there's a problem with the health of the service overall or just with one particular node. If we find that there's a problem with one particular node, then we run deeper diagnostics. And here we do things like trying to ping the machine itself, trying to ping peer nodes, trying to look at dependent services, try to create a DNS record, try to log in with live ID. All these sorts of things to sort of triangulate where the real problem is. If we find that after all of that stuff we can identify a problem, there's a warning that actually pops up in our monitoring system says, hey, turns out live DNS is the problem, or it could be that the machine just needs to be rebooted. We also, I guess I already said that. We also have a monitoring system set up so that we can monitor the service from other geographic locations. Microsoft has a service where you can actually set up an agent to run from where basically everywhere Microsoft has a data center presence. And we take advantage of that. So we have basically bits of code that are running, exercising our portal, and exercising our service itself from each data center that we have in the world. And the thing that's actually interesting about this is it gives you some insight into both latency. If you have problems that are specific to the service from just one geography, but not all of them, it gives us insight of that, alerts our operations team and our SOC for that. These things fire automatically after a period of time, after observation, and give us a lot of insight into that. So the next thing's really around sort of the security considerations or some of the attack vectors that we've thought about with the service. And you can really think of these as being on 3 different levels. At the service level, the most obvious one is that we require the channel to be encrypted. Clearly, if you don't have encryption on, you sort of open yourself up for all sorts of man-in-the-middle kind of inspection type things. TDS, frankly, is a published specification. It wouldn't be that difficult to figure out what the packet structure is, and you get the idea. So as a result of that, we do require the channel to be encrypted. We also do denial of service trend tracking. What do I mean by this? But what I mean by this is that we track the number of guys, number of connection attempts that have been made against a particular server, and we track when they failed. So you can imagine that if you're never actually completing the login process, and it's happening repeatedly over a short period of time from one particular client IP, that might be an indicator that that guy is trying to do a denial of service attack. If we see enough of those things happen and the amount of time here is configurable, then we start to block traffic from that one IP. That will reset after another configurable point of time, but the idea here is that we don't take down access to that server from everybody, but just from the guy who's just from the one bad guy, hopefully. We also do packet inspections. We mentioned earlier the gateway itself understands the TDS packet, understands the state machine associated with TDS, and therefore can make some sort of intelligent decisions about if the state transitions that are being attempted are indeed valid ones. If they're not, we'll close the connection, or if the message is not well formed, we'll close the connection. At the server level, there's a different set of things that we do. So the first is that when you actually provision a server, by default, no access is allowed to it. You have to actually explicitly grant access to your server. So there's a reason for this, and first and foremost is that by default, most people don't want their server that they just created to be by default open to the internet to everybody, right? We've made actually the administration of that bit fairly straightforward via our portal or via a set of stored procedures that we surface. We also do idle connection culling. This is more of a defense for the service as a whole, I suppose, rather than an individual server. But the notion here is that if we see a lot of connections which are just basically idle, they're not doing anything, then we will cut those connections. So obvious question comes is that, does this mean when I'm doing a long-running transaction that you're going to cut the connection? And the answer there is no. We understand where you are in the request-response pipeline, so we will never cut a connection in that case where you're just simply waiting for a response from the server. Generated server names is actually kind of an interesting one and maybe more historical than anything else. A lot of us, when we were on the SQL Server Data Services team, discovered a problem with basically squatting. So people who could create authority names like Dr. Pepper, even if they didn't have rights to that particular name. It turns out that's kind of a thorny issue, not necessarily from a technical standpoint, but more from like a legal standpoint. And that's not necessarily a great thing or something that we're interested in getting into. The second thing is that by allowing vanity domain names, it actually turns out that people are actually exposing and making themselves a little bit more open for attacks, because all of a sudden it becomes fairly obvious that, hey, that's probably a Dr. Pepper server, and maybe I'm Coke, and I want to take those guys out. So as a result of that, we auto-generate the server names. They're random, hopefully not too long where people can't remember them, but that helps a little bit as well. And then finally, on the database side, we disallow the most commonly attacked usernames. Turns out we did a little research on this. When we were first starting up the project, we actually basically put an instance of SQL Server on the net and just saw what happened over a period of time. How were people going to try to attack? What did they try to do? There's a lot of interesting things that turned out, right? So one thing is everybody tried to attack the default instance. Everybody tried to use the word essay, or user essay. Everybody tried to try root, guess, and so on and so forth. So we took that, we tried to sort of incorporate that stuff into the service itself. So those sort of obvious things, we tried to sort of prevent you from making those kinds of mistakes. And then finally, we use the sort of standard SQL sort of auth and auth model here. So to be fair, in truth, no one of these things is really the sort of the silver bullet, right? It's them in the aggregate that actually is the sort of the thing that actually makes it a very interesting thing. So I wouldn't point necessarily to any one of these things as being, that firewall thing. That's the thing that's really gonna save your service or save your database. It's really all of them working together that makes it sort of a defense in depth type thing that makes it very difficult to attack the service. So just to sort of wrap up, so we've talked a bit about sort of the general architecture of the service. We've gone through sort of the component layers, the network level topology. We've gone through how some of the provisioning process works at the server level, at the database level, and how the login process works. We've talked about service resiliency, how the service actually recovers from problems when it encounters them, and how we detect these things and try to fix them at runtime. We've talked about how do we determine service health, what are the key metrics that we're looking at to track to see if the service is healthy or not, and looked at some of the security considerations that we've taken during the design and some of the attack vectors that we thought about while designing the service. So I think if you have any of these other ones, I'd really appreciate some feedback after the talk. As always, and Dave, who was in the presentation prior to me, mentioned this, we're really sort of keen on getting feedback and evaluation. If there's specific features that you see that are missing in the service, we'd love to hear it. Also, it's my understanding that there's a charity that's actually getting some money actually for every evaluation form that's actually entered. So that's actually just a general good thing for people to do. But nevertheless, the charity for SQL Azure is just getting your feature ideas. So, and then finally, there's been quite a line for some of the hands-on labs. You can still do the labs online through channelline.msdn.com/learn. If you don't feel like waiting for the big line, I would strongly encourage you to go through that and try to get a little bit more info, not just on our service, but also on the Windows Azure service as well. And then finally, there's still a few more talks later today on SQL Azure. So Dave Robb's got his future of database development with SQL Azure, and Mark Squirrel also has one on Sync, which turns out is actually something that's quite interesting. So with that, I'll open it up for questions. If you could go to the mic, please.
Can you talk about logical server to physical instance mapping? Is there one-to-one mapping of logical server to physical server? So if I'm creating a database, is it stored on one SQL instance or is it distributed? And how is that distributed if it is?
So a logical server really is not really, it's really kind of it's really a false thing. A logical server, really, the server name is only an entry in our metadata catalog. The only things that we actually track are where the fact that it has a master database, which lives on some physical partition, and then maybe some associated user databases, which also live on physical partitions. There's really no association with a physical SQL Server instance. Yes?
On your diagram, when you showed that the databases were being created
yes.
into 3 different nodes.
That's correct.
And then when you're doing data inserts, and then so it's also going to the 3 different
nodes?
No.
No, data inserts, by that time, you're always hitting one physical node at that point.
Okay, but you're replicating that data across to the other 2 nodes as well? So
that's happening behind the scenes. So when you do an insert, actually what we'll do is, and so I guess maybe to be fair, the updates that we're doing to the replicas will be happening out of the nodes. And
right, so that's an asynchronous process?
No, that's actually synchronous.
Okay.
To at least to a quorum of the replicas.
All right. So then when I do my insert, and then when I get my response back, I can guarantee that it's actually.
That is correct. By that time, yeah, that's how we maintain consistency. Otherwise, it's really more of an eventual consistency model.
All right, thank you.
Yep. Yes?
My question regards to full client applications written, for instance, in WPF. They are, of course, not running inside Windows Azure. They are running on the client's PC.
Correct.
What do you recommend? Is it better to directly connect from the WPF application to SQL Azure? Or when should we write, for instance, a service layer in Windows Azure and from there connect to the SQL Azure? I'm a little bit concerned about the traffic because we have to pray for the traffic. And maybe you can go into that.
Yeah, that's a good, reasonable question. I think so. There's actually, so if I can tease it apart into 2 parts. There's really a client-specific piece, and then there's a bit where I have a client that maybe has some other service that I either want to coordinate or take advantage of other features. From the client piece, obviously that's just a requirements question about if a rich client is good enough for you or if a thin client is acceptable. But putting that aside for the moment, if you do have to sort of add a WCF service, I think there's actually a strong argument to be made for putting that service itself in Windows Azure. For 2 reasons. One, there's actually some caching capabilities that you might take advantage of, which would be a good thing for a real service. And that just makes all kinds of sense for that, right? You'd also lower the latency between the service itself and the database. Having said that, you're still going to incur the cost of the latency between that service and your client. But you might be able to bunch up those calls into fewer calls, hopefully, to do that. The packet size, I guess the message size is probably a wash in that case because of XML. So, but that's really your call, really, right? I think that actually makes more sense if you're composing other services together than as if you're just trying to talk to SQL Azure. Yes?
You said it right now it's using SQL user accounts only.
That's correct.
Are you planning to do anything with federation?
Yeah, so we're looking at that. Yeah, that's a common ask. Yeah. Okay. So it's 10 months. We just didn't have time. Yes?
What are the scenarios where Microsoft recommends you moving your SQL databases to Azure? Because I'm just trying to understand, is it something which is sort of available for Azure to go hand in hand with Azure applications, or is it something that could be used?
It can totally be used independently, right? I guess that there's a couple different things that drive that decision, right? And one is an operations, an OpEx cost, and a CapEx cost. I mean, you have to take a look at how much overhead do I have in managing all these databases. Turns out a lot of enterprises actually have lots of different SQL Server instances and databases that they don't even know about. So SQL Azure turns out in those cases is not only a great way to manage it, to get out of the operations and the management part of those databases, but also allows them to have some sort of global dictionary of where all those things live.
But aren't there a lot of sort of network latency related issues that
there may be, yeah, so that's a valid point. So I mean, it is remote, it's not on site, so there's always going to be some kind of latency. The hope is that if you do have apps that are running in Windows Azure, the latency is actually very small. If you're not doing that, then hopefully the sort of geographies where we're deploying our data centers to are hopefully close enough and the latency is not bad for you.
So one last thing.
Sure.
If I'm using Azure to host my application, and I also want to use SQL for my application, will Microsoft try and locate the two close together to reduce any latency issues?
So that's actually your call. So that's you as a customer can choose where you want to deploy both bits. If you want to deploy both bits in the same subregion, you'll get obviously the best performance you can. If you choose to deploy, let's say, the front end in EMEA and the back end of the SQL Azure instance in North Central or South Central, then that's kind of your call.
Sure. Thank you.
Yep.
Back to the couple of questions ago about a scenario where the SQL Azure is being accessed from code written by the customer running inside Azure as an Azure app.
Yeah.
Do you have any architectural diagrams explaining how the connectivity happens there? Is that interesting at all, or straight through?
It would be, to us, it would be no different. I guess the only thing that would be different is the point of origin of that call would be from within the Azure cluster itself.
But it still goes through the gateway, the way it's
Absolutely.
described?
Yep.
Also, it's still authenticated and validated,
Absolutely.
even though it's coming from inside.
That doesn't matter. Doesn't matter to us. Everything good.
I would have thought that you can make simplifying assumptions given that the traffic is coming from within Azure itself.
We don't trust many people.
Okay.
Sorry. Yes?
Could you talk a little bit about the characteristics of the I/O subsystem, and should I expect pretty much similar performance to like a local SQL Server system in terms of memory versus
No, I mean,
archive access or anything like that? I mean,
it's not quite the same thing though, right? I mean, so there's a bunch of other overhead that we're doing in terms of keeping your replicas up to date. As I mentioned just a moment ago for someone else, when we're doing commits not to just one instance, but to several. So the I/O characteristics are going to be different. Yes?
Yes, how will you handle patches internally into your own, either into SQL or Azure as a whole? My scenario is a patch is applied in your infrastructure overnight, and the next day, for some reason, my code doesn't like whatever went into that patch, and it takes my customers down. How do you plan on handling
patches
that?
into the OS or patches into the app?
Either really.
Yeah.
So the scenario would be something happens in your environment that I haven't had a chance to test on.
Right. So we do patch regularly. We patch it turns out on a monthly basis. In all those cases, as I mentioned before, we have a set of agents which are constantly exercising the service. So hopefully, depending on your scenario, those things should fire immediately. If they do fire, then everything rolls back.
Okay, thanks.
Yes?
On the connections, whenever I connect, you had mentioned about calling out idle
That's right.
connections. But what about connections that are doing a lot of work, and they're doing a lot of work for more than 5 minutes time frame? It seems like they get called out as well.
Yeah, so there's a throttling mechanism which we have in the back end, which says that if a transaction runs for longer than 5 minutes, those things will get killed.
Okay.
So that's still there as well. But that's independent of the idle connection calling.
Right. So like if I got a million row table that I want to use BCP to upload, that process is going to die unless I start chunking, right?
Yeah, you'd have to chunk that. Yeah.
Right.
Yep.
Okay.
Okay. Yes, over here.
So in SQL Azure, I heard that it's only 10 GB we can have the database maximum.
Presently, yes. We're going to probably raise that.
Okay. So
if you have feedback on that, just talk to me afterwards. I'd love to hear it.
Okay. And is a SQL Azure just a bunch of SQL servers replicated, or it's some other kind of memory database or something? No.
It's a customized version of SQL Server of Katmai, actually, of 2008 that we've built, and we've got a couple of extensions, not a bunch, or a couple. We have made extensions to it to support our scenarios.
Thanks.
Yes.
To a previous question, you mentioned that when a commit is done, you're actually committing the transaction to several copies. Could you explain the replication process a little bit and how that might impact performance versus what we don't currently have mirroring in our
Yeah.
SQL Server environment. How does that compare?
Yeah, so it's our own custom replication solution. But I would sort of encourage you to look at Gopal's talk for some more detail on this from last year. But in short, what happens is we receive a commit on our primary replica. We keep track of the number of total secondary replicas which are there, and we track what the mandatory quorum is for that. We then actually replay that same row data to the quorum of secondaries. And only once those guys have committed and return back, do we return back to you.
Okay, so all those commits have to take place
all of
before
them,
I get
yeah.
the response.
Yeah, because what could happen, right, is you commit to one and then a failover occurs, and then what happens is you have an inconsistent state. You don't know who to trust when you're doing leader election.
So potentially performance could
There's
degrade.
a performance impact for it, that's for sure. And that's why there's sort of all sorts of other things you need to look at. Like, I think Dave Robb went through some partitioning solutions maybe. There's different types of trade-offs one might need to do to support that.
Okay, thank you.
Yep, over here.
Curious to know what we can do about backup and restore in SQL Azure.
That's a great question.
I accidentally wipe out a chunk of data, in Management Studio or through a Duff app that,
Yeah, people make mistakes, right? I mean,
right.
So there's a couple different things, right? So first, we are looking at a clone feature, and Tony Pett talked about this earlier this week in his futures talk, whereby we can basically create a point-in-time backup to either the same server or a different server in a different geography of that, so to recover from these sorts of situations. We are actually, we've got a lot of feedback, PDC, around backup support. We're sort of really heavily interested in that, so yeah. So it's on our radar. Yes?
Any plans to support data compression in the future and also integrated full-text search?
Full-text search is interesting. We're looking at that. You're the first person that's spoken to me about compression. Have you heard that, Tony? Anything?
Yeah, a couple of things.
Okay, so evidently it's on our radar as well.
Okay.
Okay, with that, thanks for attending, guys.